Hi everybody, this is 10.1 sequences. I'm doing a modified video right now. I will leave that other video up and you can follow along with that with your filled in notes if you'd like to. Otherwise, this is just a shortened version, kind of highlights the key things, leaves out the stuff that you're expected to know from pre-calculus. Okay, so as we've learned, a sequence, right, it's basically a list of terms. It can be geometric, arithmetic. It's something that we can define recursively or come up with essentially a formula for the general term. Okay. In Chapter 10, we are going to begin the study of convergence versus divergence for series, taking a look at different tests, different ways to prove if something is going to diverge or converge without finding that exact value necessarily. So I'm jumping to Theorem 1, which is sequence defined by a function. And it basically allows us to, rather than keeping the sequence defined as it is, come up with a function that we can define it as. And then we can use all of our limit laws that we've learned over back in Chapter 2 and throughout the rest of calculus and determine whether this has convergence, divergence, or specifically what that value is that the limit would be. Okay. So the theorem states if limit as x approaches infinity of f of x exists, then the sequent a sub n equaling f of n, converges to the same exact limit. So limit as n approaches infinity of a sub n is equal to limit as x approaches infinity of f of x. So the first thing we want to do is establish a rule for the given sequence. So we have 2 squared minus 2 over 2 squared, 3 squared minus 2 over 3 squared, etc. So we could come up with a sub n equaling n squared minus 2 over n squared. And this is one where n begins at 2, which isn't something that we have to clearly define here, but it is something to note. So then based on this, we could write a function as f of x equaling, first of all, I would write it as x squared minus 2 over x squared, and I could simplify this to 1 minus 2 divided by x squared. It's not 100% necessary to do that because the way that it was originally written, we still could use properties of exponents and limits at infinity to determine what this limit would be. But when we have it written as 1 minus 2 over x squared, if it's easy enough to simplify, sometimes it's easier to go that route. So our theorem states that we can then compare the limit as n approaches infinity of a sub n and name that equal to the limit as x approaches infinity of 1 minus 2 over x squared. And if we evaluate this as x approaches infinity, then this becomes 1 minus 0, or just 1. Right? When our degree in the denominator is larger, this term always zeroes out at infinity. I'm going to bring you next example, example 4. Similar here, but this is also going to bring back L'Hopital's rule. So the way that this is presented, it almost appears as if it's a function from the beginning, but I can replace the n's with x's to make it look and feel a little more function-like. So limit as n approaches infinity of the n plus ln of n divided by n squared is equivalent to limit as x approaches infinity of x plus ln x divided by x squared. Now, I'll be honest, this step is not drastically important, right? If you're looking at me and listening to me and saying, Ms. Rod, what's the point? Nothing crazy. Honestly, if you keep it as the ends, it's fine. You can evaluate the limit. It's just making a clear-cut point that if we can define this as a function, we've already established all of these limit rules and properties based on functions, so then we're good to go. Okay, so L'Hopital, right, that was our friend that we learned in Chapter 4. And essentially, if we are in that indeterminate form of 0 over 0 or infinite over infinite, then we can derive top and bottom independent of one another. So currently, if I try to evaluate this limit, it is infinity over infinity. We might just look at those exponents and say, yeah, the denominator is going to grow faster, but we also might say, I'm not positive because there's an ln x. So why not apply the rule? Right, so now this is equivalent to limit as x approaches infinity of 1 plus 1 over x divided by 2x. And now if we, quote-unquote, plug in infinity, we get 1 plus 0 divided by infinity. So we have number over infinity, which always zeroes out. Examples 6 and 7 basically prove these to be true. We are making statements based on our geometric series. So this first one is a geometric sequence, sequence, not series, where r is greater than or equal to 0. So the base of the exponential or the geometric sequence is positive. Okay, so in the problem, it's saying limit as n approaches infinity of c, some constant, positive constant, times r to the n power is equivalent to either 0, if r is between 0 and 1, fractional. It's equal to the coefficient c, if r is exactly 1, right, makes sense, 1 to any power is still just 1. And then it is equal to infinity if r is greater than 1. It grows without bound. It diverges then, right? So if we investigate this a little bit, and we name f of r equal to c times r to the x power, specifically when r is between 0 and 1, right, then the limit as n approaches infinity of c r to the n power is equivalent to the limit as x approaches infinity of f of x, which would be basically the same thing here, but we are allowed to take the coefficient out, evaluate the limit specifically as r to the x power when r is some fractional value, right? So if r is a fraction, it's almost like having a negative exponent, right? It's flipping it, and the denominator is growing faster than the numerator. And therefore, as we go towards infinity, this will always zero out. Okay, similar argument, if r is now positive, greater than 1, not equal to, just greater than 1, then this exponential or geometric sequence would grow without bound. And if r is exactly equal to 1, then it's going to equal c times the limit as x approaches infinity of r to the x. 1 to the infinity power is still just 1, so we get c times 1 or c. So those are just proving those three scenarios. Not something that you would have to do each time. This is part of kind of the conclusions that we are going to be coming up with as we move through this chapter. Okay. Each of them continue to build on one another. Sorry, I didn't mean to skip. If we did something really similar, this page, this is the one that I want. If we do something really similar now, when r is less than 0, right? So the setup for this is almost the same. The constant cannot be 0, so therefore this geometric sequence actually exists. The two scenarios hold true, and that's what we're going to prove. So if r, which is a negative value, is between -1 and 0, which still means fraction, right? Then it's going to zero out. And we'll show that with the same exact logic, honestly, because if we have a fraction, whether it's positive or negative, raised to infinity, your denominator grows without bound, and therefore the fraction zeroes out. And if r is less than or equal to -1, so it is an integer, what's going to happen here is it's going to diverge, because having that negative value then changes the sign of the outcome, right? So if we have odd powers, the negative holds there. If we have even powers, then we're going to end up having positive values. So the absolute value of CR to the n grows very large. But if we keep that negative in there, then it alternates in sign, kind of like an oscillation. So let me just write down everything that I was just saying. So we're using that same function, CR to the x power, specifically when we analyze between 0 and -1, which is a fraction, right? The limit as n approaches infinity, whether it is positive or negative, in this situation, doesn't change anything. No matter what, it is a fraction. The denominator is growing without bound, and therefore it will zero out. So this would be exactly equal to if I did the same proof without the absolute value signs. Okay. I cannot do this and make a true statement when r is less than or equal to -1. So we are just basically making the conclusion that odd powers will grow to -infinity. Even powers will grow to positive infinity. So it is alternating in sign. And therefore, it is diverging. So it's either not getting a value or it is a value of infinity or negative infinity. I'm going to take you to this page. Truly nothing new here. Limit laws for sequences. So because we're treating these sequences like they are functions, we can add or subtract them, and then therefore, if their limits exist and equal some value L and M, then we can add or subtract those answers. We can multiply and multiply their answers. We can divide, given that the limit of b sub n as n goes to infinity is not 0, then the fraction of L over M would be the answer. And then we can also multiply by any coefficient, any constant. Okay? So these are nothing new, nothing that you need to, memorize all of a sudden because you really have that skill set already. And then our friend, the squeeze theorem, finally comes back, right? You've been asking me, well, you have asked me, not so much recently, but, when would we ever use this? This is one more application where you're going to see the squeeze theorem come up a little bit. It's still not, as monumental as we might have thought it could be or some of our other theorems have been, but at least it's coming back one more time. All right, so let's apply it. And this one's a little bit complicated, so kind of bear with the logic here. We are proving that the limit as n approaches infinity of r to the n power divided by n factorial is equal to 0 for all values of r. Okay. So for this proof, we're going to assume that r is positive. And we're going to choose another unknown value, m, and just say that m is also a positive integer. I'm allowed to do things like this because I'm specifically forcing the squeeze theorem, right? I'm looking for two values, upper, lower, left, right kind of thing, in an inequality that result in the same answer essentially and force the given sequence, in this case, or function, to therefore have the same output. So you might be like, well, the problem says all are. True, but I only have to show it in this way, and as long as I'm able to literally squeeze two things and have the same result on the left and the right of my inequality, then the original sequence function must also take on that same value. So based on r being positive, m being positive, I could come up with something that says this. R is greater than or equal to m and less than m plus 1. Could be a true statement, right? r just has to be larger than 0, and then, sure, I could find an r that is between two positive integers. Okay. So now, if or for n, referring to the amount of kind of times that I list out my sequence, amount of terms, for n being larger than m, this is important. Okay, let's take a look at exactly why this is important. So n, the amount of terms that I'm listing, is larger than m. Then r to the n power divided by n factorial would equal the n being larger than m, and as well as the r being larger than m. So this sequence is equivalent to r to the first over 1, not plus, I'm sorry. Okay. Times r over 2, right? My denominator is the factorial, the numerator is the repeated multiplication. Times, I could continue this as many times to just show what's happening, dot, 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 up until r over m. I'm choosing to chunk this right here because this value right here is something that is larger than 1. Larger than or equal to. Because we established the fact that r is greater than m. So then r being greater than m, greater than or equal to m, means that right at that moment, r over m, that is still a number larger than 1. So every fraction prior to that is a number larger than 1. So the multiplication, the product of that, is a number larger than 1. So I can name this some constant c, and I know that it's greater than or equal to 1. Okay, I'm not done here, right? Because I said that I was going to n. So my next terms are r over an m plus a 1, r over an m plus a 2, all multiplication still, dot, 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 until I get to r over n. This is technically the smallest term, right? N is now the largest value, making the overall fraction the smallest. Each of these factors is less than 1. Factor or term. Right. And therefore, the product must also be less than 1. And more importantly, not just less than 1, less than the very last term, r over n. Right? Each of those individual r over m plus 1, r over m plus 2, etc., is a fraction less than 1, getting smaller and smaller and smaller. If I multiply fractions together, the product gets even smaller. So that product is less than r over n. So I can conclude here all of this, right? I chunked it into those two sets of large brackets because then I can name that first chunk C, and then that last chunk, right? I'm using an inequality sign, so everything on the left-hand side is less than or equal to C times r over n, because the product of my second set of parentheses is less than r over n. Okay? So now I'm trying to prove 0. So 0, which has to be smaller than or equal to r sub n, r to the n power over n factorial, right? Because we're plugging in positive values. So we're not going to get a large answer, but we're getting something positive. And r sub n over n factorial, we just proved, is less than or equal to c times r over n. And if I take the limit as n approaches infinity of c times r over n, well, can I just prove by plugging in infinity that this is equal to 0? And if both sides of that inequality sign are 0, the squeeze theorem then proves that the original, I'm running out of space, but the original limit as n approaches infinity of r to the n power over n factorial is also 0. Just a couple more examples. Okay, so theorem 4 states that if f of x is continuous and the limit as n approaches infinity of a sub n is equal to L, we can essentially do the composition of these two things, right? We're taking the given sequence and inputting it into the function and taking the limit of as n goes to infinity. Because of our basic limit laws, we are allowed to, I'm not coming up with the right word here, but extract, right? Extract all operations from our limit so that we directly apply the limit to the input, the x, quote unquote, the sequence in this case. We did this, think back specifically, we did this, and it was a little bit funky at first, when we applied that e to the ln so that we could use logarithmic differentiation within a limit. So that was one of those moments where it's like, how are you pulling this e out and putting the limit on only the exponent? Same idea is going to happen here. Okay, so what I mean by all of that. In this example, a sub n is given as 3n over n plus 1. F of x is equal to e to the x power. And we are using this theorem 4. So example A would then say f of a sub n is equal to e to the a sub n, which is equal to e to the 3n over n plus 1. Right? And the theorem then says, well, if I want to take the limit as n approaches infinity of this thing, right, this is equivalent to, pull the e out of there. The e is not where the input is. We're taking the outer, or the composition portion of it, and directly applying the limit to that input. Not forgetting about our e, that will come up in our final answer. Then we can say, based on exponent properties and limits at infinity, our degrees are the same, so we take the ratio of the coefficients. So the limit is equal to 3 here, and our answer then is e cubed. Okay. Part B, very similar. The function is x squared, so the function written with the sequence becomes 3n over n plus 1 squared. So the limit as n approaches infinity of this g of a sub n is equal to, well, let's bump that squared out, that operation out of there. So quantity, limit as n goes to infinity of 3n over n plus 1 squared. Well, we already took the limit. It's the same thing. So that limit still comes out as a 3, and now we square the result. So we get 9. So this is true if the function is continuous and the limit as n approaches infinity of the sequence equals, some real value, L. All right, last example here. This idea of having a bounded sequence, I think of this as sort of a floor and or a ceiling, or horizontal asymptotes. So if we are bounded from above, that's kind of my ceiling metaphor. we have this number, capital M, such that the sequence, the a sub n, is smaller than or equal to m for all n values, no matter what you plug in. Real life example, what if we had like a maximum population, for example, right? Then that number m is called an upper bound. Bounded from below, if there's some lowercase m, some number m, such that that sequence is never going to go below it. It's always larger than or equal to it. The number m is then called the lower bound. Okay, so ceiling and floor is my metaphor there. The key is they're not guaranteed values. It doesn't mean that the sequence has to converge to that m, but it can't be larger than it if it's a upper, if it's bounded from above, and it can't be smaller than it if it's bounded from below. Convergent sequences are bounded, right? That's just a given, right? If we've proven something that's convergent, there is a bound to it. And then this one's kind of cool. Bounded monotonic sequences converge, but they're very, very specific. If a sub n is increasing and bounded from above, then it converges. Increasing bounded from above proves convergence. Increasing bounded from below is meaningless. Right? If we have a horizontal asymptote, but the function's growing forever, and the horizontal asymptote is below the growth of it, doesn't matter. If a sub n is decreasing, right, and bounded below, then that proves convergence. So let's use example 11 to kind of show this here. Verify that a sub n equaling square root of n plus 1 minus square root of n is decreasing and bounded below. Well, how do we show that a function is decreasing? We take a look at our first derivative test. We want to see, is that first derivative negative? Okay. All right, so f prime, if we think of that sequence as a function, is equal to a half quantity, change that to an x plus 1, to the negative 1/2, minus 1/2 x to the negative 1/2, or 1 over 2 square root x plus 1 minus 1 over 2 square root x. The second fraction is larger because the denominator is smaller. Therefore, this is negative always when x is positive, which is all we care about because we're looking at the positive infinity side of things. When x is negative, it's not defined. Okay. So in the textbook, I'm not going to pull it up here, in the textbook they do show some table values for each of a sub 1, a sub 2, a sub 3, etc. And you'll see that those values do begin to converge. They level off, they plateau, they meet an asymptote essentially. It's showing that they're decreasing. The other thing, we've gotten enough. We don't need to show the actual value that it converges to. All we're looking to do is prove that that limit as n approaches infinity exists. So because a sub n is positive, we did see a lower bound. The table shows a lower bound. Specifically, 0. And if we thought about this without having a table of values, that makes a lot of sense, right? If we have two square roots, the smallest value that n could be would be 0 there. So theoretically, we could get square. Let me hold my thought for a second. Okay, yeah, actually using 0 is not the right example. If I just picked a value of 1, right, then the square root of 2 minus the square root of 1 is smaller than if I chose 0. So anyways, the lower bound is approaching 0. but not necessarily hitting it. And that's all that we needed to show. If we have a lower bound and we are decreasing, therefore the limit as n approaches infinity of a sub n converges. That's the key. We didn't need to come up with a value. Does it exist? So in summary, this is all kind of the bullet points that we went over in this lesson. Pretty much this is kind of a foundation for where we're headed. I can put the homework here if that's helpful. Page 546, numbers 3, 5, 9, 13, 14, 17, 27, 37, 45, 51, 61, and 60.